In this video, I am going to discuss the relationship between unit matrix and identity operator in point groups. If we have a symmetry operator, say R, and multiply it with its own inverse or inverse, then we get the identity operator E. So if we can somehow represent this operator by a matrix M and this operator by another matrix, say M primed, then product of these two matrices should give a matrix that will represent the identity operator. So let us try this with an example. I have taken here the example of the BF3 molecule. The fluorine atoms have been labeled as 1, 2 and 3, and the boron atom is labeled 4. It is a planar molecule. The plane of the molecule is a symmetry plane, and it has a threefold rotation axis like this, perpendicular to the plane of the molecule and passing through the boron atom. We can rotate this molecule and we'll get equivalent configurations. A C3 operation means 120 degree rotation about this axis in an anti-clockwise direction. We'll apply this rotation to the molecule and see its effect on the 2s orbitals of all these atoms. Let phi1 denote the 2s orbital of fluorine labeled 1, phi2 is the 2s orbital of fluorine labeled 2, phi3 is that of fluorine labeled 3, and phi4 is the 2s orbital of this central boron atom, which is labeled 4. Suppose that after a C3 operation, these are actually functions, wave functions of the orbitals. If we apply a C3 operator on the ith orbital, suppose it becomes a new function, phi I primed. This is for all the 4, 1, 2, 3 and 4. This means that C3, phi1 turns into phi1 primed by C3, phi2 turns into phi2 primed, and so on. So this diagram now indicates that phi1 primed is actually what? This atom comes here by this rotation, anti-clockwise rotation, and the 2s orbital is spherically symmetrical. Therefore, phi1 primed is actually phi2. The 2s orbital of this atom goes to this position, so phi2 primed, the new form of phi2 primed of phi2 is actually phi3. New form of phi1 is actually phi2. Similarly, phi3 primed, 3 goes to 1. So the new form of phi3 is phi1. And what about phi4? Phi4 does not change. Phi4 primed is phi4 itself, because it is at the central position, it is situated on the axis of symmetry, and the 2s orbital is spherically symmetrical. So phi4 primed is phi4. These four relations can now be expressed in the form of a matrix like this. Suppose we are writing the initial functions phi1, phi2, phi3 and phi4 in a column, in the form of a column matrix. It is a 4 by 1 matrix, 4 rows, 1 column. This is the initial set of orbitals, and we want the final set of orbitals also in the form of a column. This is a 4 by 1 matrix, phi1 prime. These are the new functions. What is the relationship between these two matrices? How can we get this matrix from this one. We have to multiply this matrix by some other matrix. This is a 4 by 1 matrix, and we have to multiply this by another matrix. What should be the size of that matrix? That matrix here should have 4 columns, because this number and this number must be equal. So this matrix has to have 4 columns. And finally we want a 4 by 1 matrix. So this matrix should be a 4 by 4 matrix. Upon multiplication we will get a 4 by 1 matrix. So here we need a 4 by 4 matrix for transforming this set into this set. Now I have redrawn the diagram here for convenience. Phi 1 primed is phi 2. We have the relation phi 1 primed equal to phi 2. So the first row here, phi 1 primed is on the first row. So the first row should have 1 at the second position, because we need phi 2 here. The other positions of this row should be 0. If we multiply this row by this column, our result will be phi 2. Similarly phi 2 primed is phi 3. Phi 2 primed is phi 3. So in the second row, we need phi 3. Therefore, the second row should have 1 at the third position and 0 at the other positions. If we multiply this row by this column, 0 into phi 1 plus 0 into phi 2 plus 1 into phi 3 plus 0 into phi 4. That will be equal to phi 3. This relation is given by this matrix product. Similarly, phi 3 is phi 1. Phi 3 is phi 1. So third row will contain 1 at the first column, 1, and the other columns will be 0. Similarly, what is phi 4? Phi 4 primed is equal to phi 4. So we need phi 4 here. Therefore, the fourth position should be 1, and the other positions will be 0. If we multiply this row by this column, we will get phi 4. Phi 4 prime will be equal to 5. So these 4 relations, actually these are 4 linear relations. Phi 1 primed is 0 into phi 1 plus 1 into phi 2 plus 0 into phi 3 plus 0 into phi 4. This relation can be written in expanded form like this. And similarly, phi 2 primed is phi 3. Phi 3 means 1 into phi 3. The other coefficients are 0. 0 into phi 1 plus 0 into phi 2 plus 1 into phi 3. If we write these relations in the form of 4 linear equations, then the coefficients of the right hand side have been written in the rows of this matrix, and these functions have been written in one column. This is how this matrix is constructed. And this matrix is called the matrix form M of the operator C3 in basis phi 1, phi 2, phi 3, phi 4. Basis, this is the terminology used. Basis means a function or a set of functions or a set of vectors on which a symmetry operator is to be applied in order to get a matrix form for that operator. The term basis set will be very often used in applications of group theory. In the same analogous manner, we can construct a matrix for the inverse operator. This is the matrix for the C3 operator. This is the matrix for the C3 operator, and we can construct a matrix for the C3 inverse operator. C3 inverse operator. C3, I have redrawn the diagram here. Suppose by this inverse operation, the functions become double primed. Phi 1 becomes phi 1 double primed, phi 2 becomes phi 2 double primed, and so on. C3 inverse operation is a rotation in the opposite direction. Now the rotation will be in the clockwise direction. So phi 1 becomes phi 3 by this rotation. So phi 1 double prime is equal to phi 3, and therefore in the first row we will write 1 in the third column and 0 in the first two columns. Similarly, phi 2 double prime on this rotation becomes phi 1. Therefore, we will write 1 in the first column in the second row and 0 in each of the other columns. Phi 3 double primed becomes phi 2. So we write 1 in the second column and 0 in the other columns. Phi 4 double primed is phi 4 itself. So we write 1 in the fourth column and zeros in the other columns. This is the matrix for the C3 inverse operator in basis phi 1, phi 2, in the same basis phi 1, phi 2, phi 3, phi 4, same basis set. Let us now test whether this is correct or not. This matrix form for each of the operator is correct or not. I have collected the matrices. The matrix for C3 is this one, and matrix for C3 inverse is this one. These two have been just constructed, and we will multiply these two matrices, and we expect that the resulting product matrix will be a representation for the identity operator. First, test the compatibility for multiplication. This is a 4 by 4 matrix, and this one is also 4 by 4. So these two numbers are equal, and after multiplication we will get a 4 by 4 matrix here, 4 by 4. So these two matrices are compatible for multiplication. Now multiply this row by this column, you will get a number here. 0 into 0 plus 1 into 1 plus 0 into 0 plus 0. So you get 1 here. This row multiplied by the second column will give you 0. This row multiplied by the first row multiplied by third column will give you 0 again. 0 into 1 is 0. 1 into 0 is 0. 0 is etc. So this will be the result in the first. Now take the second row. This row multiplied by this column, first column, will give you 0. This row multiplied by this column will give you 1, because 0 into 0 plus 0 into 0 plus 1 into 1 plus 0 into 0. So you get 1 here, and the other positions will be 0. In this way, if we carry out the multiplication, we will get a matrix like this. Fourth row multiplied by the fourth column will give 1 here. Thus we see that this is a diagonal matrix having 1 at all the diagonal positions and 0 at all the other positions. This is the identity matrix or unit matrix of size 4 by 4. So the matrix for the identity operator is this unit matrix of size 4 by 4 in basis phi 1, phi 2, phi 3, phi 4. We say that all these matrices are 4-dimensional representations of the concerned operators. This is a 4-dimensional representation of C3 operator. This is a 4-dimensional representation of this inverse operator, and this is this unit matrix of size 4 by 4 is a 4-dimensional representation of the identity operator. And we also know that trace of this identity matrix is 4. Trace of the identity matrix for the identity operator is 4, which is equal to the number of basis functions used. This is what I wanted to explain today. We will get more and more examples of different symmetry operators in matrix forms, and in all cases we will find that the identity operator is denoted by the unit matrix of dimension n, where n is the number of basis functions or vectors used. I thank you very much for watching this video.